This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today, I am going to discuss the programming for 8086 under microprocessor and microcontroller subject. In this session, I am going to explain how to find in a given series how many number of even numbers are there, odd numbers are there. That is first program. The second program is about how many number of positive numbers and negative numbers are there in a given series. The third one is if you given a 32-bit data, that is multi-byte data, to find whether it is consist of even parity or odd parity. The slides are prepared by referring the textbook Advanced Microprocessor and Peripherals, authors A.K. Ray and K.M. Burchandi, publication Tata McGraw-Hill Education. So the first one is write an ALP to find an even number or odd number in a given series. So here in the data segment, we are going to take a few numbers. Let us assume I'll take the number 1, number 2, number 3, number 4. For each and every time, we will fetch one data. Whatever the fetch data is there, that we will check whether it is even or odd. So for finding out a given number, whether it is in the even number or odd number, in binary system, we are going to see the LSB value. If you examine the LSB value, it is sufficient to decide whether it is a even number or odd number. No need to go for dividing by 2 and finding out whether it is remainder is 0 or not. If it remainder is 0, even number, and remainder is non-zero, it is odd number. Here, in the binary format, by checking the LSB bit, we can decide whether it is a even number or odd number. In the binary format, the LSB, if it is ending in the LSB with a 0, it indicates it is an even number. If it is ending with 1, it indicates an odd number. So what we will do is, we will take one data, we will shift the contents or rotate the contents towards right side by 1 bit. So when you shift these contents towards right side by bit, what are the data which are going to be considered? When you shift, the B0 bit will be moved to carry flag. So by checking the carry flag, we can decide whether it is even number or odd number. If carry is equivalent to 0, it indicates the given number is a even one. If carry is equivalent to 1, it indicates the given number is a odd number. So this is what the logic which we are going to employ for writing a program for finding out even number or odd number. So in the data segment, let us assume if I have 4 numbers, so how many numbers we have to check, that we are going to write this one as a count. Now coming to the program. So first we will clear a register, a BX. The purpose of the BX register, we are going to be take one register will allot for even numbers, another register will be allotted for odd numbers. As BX is consist of 2 registers, BL and BH, one register will reserve for even number, another register will reserve for odd number. So even count we are placing in BH register, odd count we are going to be placing in BL register. Even count BH, odd count BL register. So for that purpose, first initially we are clearing the BX register, then we are reserving BL register for odd number of ones, and BH is for counting how many even numbers are there in a given series. Next, how many values in a given series, how many values we are going to be take, that we are taking as a count which will be there in the memory of the data segment. So this count we are going to be load into SL register. CL. So let us consider I have 4 numbers N1, N2. In the example which we are going to be take is a series consist of 4 numbers. So it is having in the data segment N1, N2, N3, N4. This is the given series. Beneath to this, we are going to have count where count is equivalent to 0, 4. Then we are going to reserve the memory for even numbers and odd numbers. This is what the data segment which we are using for this particular program. Next, this count we are going to be load into CL register. So after executing this instruction, the CL value will be 04. Next, LEA SI comma series. So this instruction is used for loading the effective address of the series variable. So these numbers N1, N2, N3, N4, these 4 numbers we are taking as a series. So where the starting address is 00, that we are going to be load into SI register. So for the initial iteration, so SI value default is 0 will take. Next, in this memory location at 00H, whatever the content is there, that we want to load into AL register. So for that we use move AL comma in brackets SI. So what this instruction is going to do is, for each and every iteration, in the first iteration N1 will be copied into AL, in the second iteration N2 will be copied into AL, in the third iteration N3 will be copied into AL, in the fourth iteration N4 will be copied into AL. So each and every iteration it is going to fetch one element of a series. Once the data is available in AL register, then we are going to shift these contents towards right side by 1 bit. So when the AL contents are shifted towards right side, the LSB bit will be moved to carry flag. So first we are doing the shift operation, that is logical right shift of the AL contents by 1 bit, so that the LSB bit will be moved to carry flag. So by checking carry flag, we can decide whether it is even number or odd number. So for checking the carry flag, we are going to use the instruction is JC, which indicates jump if carry. So if that means if carry is equivalent to 1, go for label 1, otherwise subsequent instruction. So what is carry is equivalent to 1 specifies, what is carry is equivalent to 0 specifies. When carry is equivalent to 1, it indicates the given number is a odd number. If carry is equivalent to 0, it indicates the given number is a even number. So when we check the carry flag, go to the label 1. So at label 1, we will write the logic for odd numbers. Suppose if carry flag is equivalent to 0, that means if the given value is even number, then we will go to the subsequent instruction. As the condition fails here, it will come to the next instruction. In the next instruction, what we are having? Increment BH. So why we are incrementing BH here? It is BH we are reserving for finding out how many number of even numbers are there in a given series. For each and every even number encountered, it will be increment the BH. Increment BH. Then go to L2, where L2 will go for further operation. As we have checked one number and it is decided as even number, the subsequent operation we go for addressing to the next memory location. As we have checked one number, we are going to decrement the count. That subsequent instructions will be there. Suppose if carry is equivalent to 0, the control will be transferred to L1. So what the L1 is doing? Increment BL. So why we are incrementing BL is BL register we are reserving for holding the number of odd numbers which are present in the given series. So for that we are going to be increment BL register. So in these two cases, this is step for incrementing even numbers and this is the step for finding out or incrementing the odd count. So once you are done this, then we have to progress for the second number. So in this first iteration, N1 is checked. You have decided whether it is even or odd. If it is even, increment the BH counter. If it is odd, increment the BL register. As one data is done, I want to advance to the next data. So whatever the address we are having, for advance to the next one, we are going to be increment the SI value. So why we are incrementing is because the address for N1 is 000 and the size of data which we are going to be considered is only 8 bits. So one memory location is reserved for N1. The next memory location, that is 001, is for N2. So we have to increment this address by 1. So for that we are writing the instruction is increment SI. So once the increment is done, then again we need to go for iterating. So that will be done by checking whether the given number of count that is loaded in CL register, whether it is non-zero or not. So what is the CL is consist of? How many number of ones are there? Whenever you check a particular number, we are going to decrement that particular count in CL register. So as one number is checked, we are going to be decrement CL. If CL is non-zero, so what is CL indicates? It is having some count. So when CL is equal to 0, it indicates all the numbers are checked. Still, if CL is non-zero, it indicates still we have few more numbers to check. So go for checking next number for even number or odd number. So decrement CL. Then we go for checking whether the CL register is a 0 or non-zero. So for that we go for J and Z instruction. So what is J and Z indicates? If it is non-zero, the Z flag is 0. If CL is equal to 0, Z flag is set to 1. So when we want to go for next number checking, if count is non-zero, that means Z flag is equal to 0. So that's why here we are checking J and Z. If it is non-zero, then only go to loop 3. So in the loop 3, what is the next activity we have to do is again fetch the content from SN. So L3, you can see here, L3 is given for this instruction. L3. L3 move AL comma SI. Suppose if the count is 0, that means all the numbers are verified, whether it is a even number or odd number, corresponding count also incremented. Then I want to load this count which are there in BL register and BH register into the memory. As we have said earlier, in the memory we are reserved two memory location. One is for even count, another one is for odd count. So now I want to move the count into this memory location. So how to move the content into this memory location? Before that, we had to fetch what is the address of it. What is the address of it? So for fetching the address, we use the instruction load effective address, that is LEADI comma even count. So what this instruction will do is it will fetches the address of the even count that will be loaded into DI. Once the address is fetched into this, we have to load the BH register contents, because already BH register we are reserved for even number of count. So then we go for writing the BH contents into the memory location. So whose address is loaded into DI register. So move in brackets DI comma BH. So this instruction will load the number of even numbers in a given series which are present in BH register into the memory location. Next, once the even count is done, then we have to load odd count. For loading the odd count into this memory, we have to fetch the address of this variable. So for that we use LEADI comma odd count. So this instruction will fetch the address of the odd count that will be loaded into DI. So into this memory location, we are going to load BL register, as we are assigned the BL register is for holding the number of odd numbers present in the given series. That count we are going to be loaded into memory location where the memory address is placed in the DI index register. So with this, the program is done. Then as we are executing this assembler program on DOS prompt, we have to return to the DOS. So for that, we will write move AH, 4CH, INT21H. So this is a software interrupt type 21 and the subroutine having the value is 4CH. It is for indicating to after execution. Again, for returning to the DOS prompt, if you are using assembler, we are going to use these instructions. If you are using any another assembler, accordingly we have to write. If you use Win862, we can write these two instructions with INT03H. So in the consolidation, I'll explain the brief program at a single place. So assume CS colon code DS colon data. So here assume is a assembler directive which is for requesting for memory for two segments. One is code segment and the one is data segment. So whatever the address which is assigned by the assembler, that will be there in CS and DS for code segment as well as data segment respectively. Next, we are going to be define a data segment. In this data segment, so whatever the values which we are going to be placed in the data segment, for that we will write the data segment. So segment is a assembler directive to indicate the start of a segment. What type of segment we are starting? Data. So we will write data segment. Next, to end this segment, we have end-s. End-s indicate end of the segment. Which segment we are ending here? Data. So in between that, whatever the values are there, that it will be placed in the data segment. So let us assume this is what the entire memory. Assume this is the data segment which is reserved by the assembler. So now in this we are going to be placed first series. A series is a variable name. This series is consist of 4 values: 65H, 89H, ABH, 52H. So these values I am declaring as a series variable. As the size of each and every data is 8 bits, we are using a directive that is a DB, which indicates a defined byte. So when we write this statement, so 65 will be loaded in the first memory location, 89 will be loaded in the second memory location, AB will be loaded in the third memory location, 52H will be loaded into the next memory location. So after that we are going to be load count. So count also will be loaded with the value of 04. Next we are reserving 2 memories, that is even count and odd count. So to reserve the memory we are going to use the DUP. A DUP is a assembly directive which indicates you are reserving some memory. How much memory you are reserving? One data I am having, the size of this data is 8 bits. That means we are reserving one memory location for even count. As it is uninitialized, we are going to place this one in a question mark. Similarly for odd count, we will write the directive as odd count, DB, 01H and DUP question mark. So these two are for only reserving the memory. No data will be stored in those places initially. Next, as we are ended the data segment, we will write data ends. Next, in the code segment, start. So first we have to load the segment address which is assigned for the data segment into the DS register. So for that we'll write move AX comma data. So here the data is holding the address of the data segment. That we have to load first into AX register, from AX register to DS register. Directly we can't write the immediate data into the segment register. First we have to load into AX register, from AX register to data segment register. Then clearing the BX register, which is used as a counter for even numbers and odd numbers, BH and BL respectively. Then how many elements are there? That we are going to be write as move CL comma count. Next, for fetching the address of first element, LEA, that is load effective address, SI comma series. So the address of this series variable will be loaded into SI register. Then we go for checking move AL comma in square braces SI. That means we are referring the source content in the memory location whose address is specified in SI register. That memory contents will be loaded into AL. Then we go for shifting the contents towards right side by 1 bit. So when you shift the contents of AL towards right side by 1 bit, so the LSB value will be moved to carry flag. So here we are going to check carry flag is either it is 1 or 0. If carry flag is equivalent to 1, it indicates it is an odd number. If carry flag is equivalent to 0, it indicates the given number is a even number. So for that we will write JCL1. So in the JCL1, the control will be transferred to L1 if carry flag is equivalent to 1. So what is carry flag is equivalent to 1 specifies the given number is a odd number. Suppose if carry flag is equivalent to 0, that JC instruction will be skipped and next instruction will be executed, that is INCBH, which is for incrementing the count which is related to even numbers. Then we go for unconditionally jump to L2. Why we are skipping this increment BL is, increment BL it is for only updating for odd count. Next, either it is even number or odd number, after updating the corresponding register, then for pointing to the next memory location, that is for next data, we go for incrementing SI, decrement the count, because still how many numbers we are checking, that will be there in CL. If it is non-zero, go to label 3. So what is label 3 we are going to have is fetching the data into the AL register and checking back. So this will be repeated until the CL content is 0. Once the CL content is 0, that indicates the given series is checked for even numbers or odd numbers. So then we can store the count which we are there in BX and BL into the even count memory and odd count memory. For fetching the address of even count variable, so we use the instruction LEA DA comma even count. So this instruction is used for fetching the address of even count that will be loaded into DI. Into this memory location, we are going to be load the count which is there in BH register. For addressing to the next memory location, which is for odd count, either you go for incrementing DI, otherwise we can go for again the same instruction like LEA DI comma odd count. Any one of these instruction we can use. Then the odd count which is there in the BL register, that will be loaded into the given memory location. Then we can terminate the program by raising INT21H interrupt, which is for returning to the DOS prompt. The subroutine we are having the value is 4CH. Then to end the code segment, code endes. To end the program, end is the directive. So which one we have to end, which is given with the label start. So this is the program to find a given series. Either it is consist of odd numbers and even numbers. If odd numbers are present, how many odd numbers are there? How many even numbers are there? Next, we will move to the next program. The next program is corresponding to find a positive number or a negative number in a given series. So write an ALP to find the even number or odd number in a given series. So here also we are going to be considering a data where it is consist of few numbers N1, N2, N3 and N4. So we are going to check N1 number, whether we will decide whether it is positive number or a negative number. Then accordingly we will increment the count. Similarly, after checking N1, then we go for checking N2, N3 and N4. Right, now here the logic for knowing whether the given number is odd number or positive number or negative number is, in the data, just if you check MSB, we can decide whether it is number is a positive number or negative number. If MSB is equal to 0, it indicates the given number is the positive number. If it is 1, the given number is a negative number. No need to check for comparing whether it is greater than 0 or not, or less than 0 or not, for deciding whether it is even number or odd number. In the binary format, for a signed number, MSB is reserved for sign. If sign bit is equivalent to 1, it indicates it is a negative number. If sign bit is equivalent to 0, it indicates it is an odd positive number. First, we will clear BX register by using the XOR instruction. All these programs which we have discussed for finding out even number or odd number is same. Only one instruction will be changes. For checking whether it is a even number or odd number, we have checked LSB. Whereas for sign, we are going to be check the MSB. Only one instruction will be changed. Rest of the program is same as that of the previous program. So first we will clear the register XOR BX comma BX. How many numbers we are checking in a given series, that count we are going to be loaded into CL register. To fetch the address of the series variable into SI register, we use the instruction LEA, that is load effective address of the series variable into SI register. Next, once the address is fetched, we will fetch the data in that memory location by using move AL comma in square braces SI. So this will refers to a memory location. In that memory location, whatever the data is there, that will be loaded into AL register. Once the data is there in AL register, we want to check the MSB. So for checking the MSB, we will shift these contents towards left side by 1 bit. When we shift these contents, then MSB bit, that is B7, will be loaded into carry flag. So what is carry flag is equivalent to 1 indicates the given number is a negative number. If it is equivalent to 0, it indicates the given number is a positive number. So after shifting the contents of AL register towards left side by 1 bit, then we go for checking what is the carry flag value. So for that we use the instruction is JC jump if carry. So what is carry is equivalent to 1 indicates a negative number. So if it is a negative number, go to label 1. In the label 1, we go for incrementing BL register. Suppose if the given number is not a negative number, that is a positive number, then this condition fails, the next instruction will be executed. So that means if carry flag is equivalent to 0, which means a positive number, then we go for incrementing BH register. So this BH register, it is for positive number, BL register is a positive number. Once the corresponding count is incremented, then we go for addressing to the next data by incrementing SI. Then as one number is checked, then we go for decrementing the count, which is there in CL register. So what is CL register is equivalent to 0 indicates all the data has checked. So you can terminate the program. If CL is equivalent to non-zero, what indicate is still the next data we want to check. So we go for iterating if count is non-zero. So when count is non-zero, jet lag is equivalent to 0. If CL is equivalent to 0, count is going to be 1. So when we are going for next data, if jet lag is equivalent to 0, so for that we will write the instruction is JNZ. So when 0 flag is 0, go to loop 3. So where we are going to be placed loop 3? Loop 3 will be placed for fetching the data from the memory location into AL register. Suppose if CL is equivalent to 0, what it indicates? All the data has been checked for either even numbers and odd numbers in a series, updated the count respectively. Then we go for moving the corresponding data into the corresponding locations. So for that you'll write LEA comma, this is a positive number, positive count. The address will be fetched into DI register. The BH count which is loading or which is holding the positive numbers, that will be loaded into memory location. Next we go for fetching the address of negative numbers, that is LEA DI comma negative count. So when you fetch this count, when you fetch the address of negative count into DI into this memory location, we are going to move the negative number counts which are there in BL register. So once these two memory locations are updated, we can terminate the program to return to the DOS by executing or generating interrupt 21 type by calling the subroutine with the 4CH. Now we will see the entire program in a single glance at a time. So assume CS colon code, DS colon data. This is for requesting the assembler for reserving the memory for code segment and data segment. Next, segment is a assembler directive which indicates the start of a segment. Which segment we are starting, that will be preceded here. So as it is consist of data segment, it indicates it is a start of data segment. So in this data segment, what we are placing is first a series variable is placed. The values in this one is 65H, 89H, ABH and 52H. Here the size of each and every data is 8 bits. So we will define this one with the assembler directive DB, which will define byte. Next, how many values we are having here? 4. So this we are going to be placed in the count variable with the value of 4 in the next memory location. So count DB04H, as it is reserving one memory location for count. So the size of count variable is a DB, which is 8-bit size. After this, we are going to be reserved two memory location. One is for positive numbers, another one is for negative number. So positive number, the next memory location, negative number, the next memory location. Then we will end the data segment with the end dash directive. End dash directive, it is for ending the segment. This segment we are ending data. So we will write this one as data end dash. Then the start of the program by using the segment assembler directive. Segment is a assembler directive to indicate the start of a segment. Which segment we are starting here, that will be preceded here. So we are starting here code segment. So first the address of the data segment which is reserved by assembler will be exist in the data variable, that we are going to be load into DS. So as it is an immediate data we can't load directly into the data segment. So first we have to load into AX register. From AX register to we have to load into the corresponding segment register. As it is a data segment register, so AX contents which is loaded with the address of data segment, that will be moved to data segment register. Then for clearing the register, we will write XR BX comma BX. So the XR operation, it is for clearing a BX register. So why we are clearing a BX register is we are allocating the BL register and the BH register for holding positive numbers and negative numbers. So initially we will clear the register. Then for fetching the address of the series variable, we use the instruction is LEA, where LEA stands for load effective address. The address of this series variable will be loaded into SI. Then L3 is equivalent to move AL comma SI. So what this instruction is used for fetching the data from the data segment whose address is there in SI. So this memory contains, for each and every iteration, it is going to fetch one data at a time into AL register. Once the data is fetched, then we are going to be shift this contents towards left side by 1 bit. So for that, you will write the instruction is SHL AL comma 01H. So for checking whether it is positive number or negative number, we have to check MSB. For checking MSB, shift this contents towards left side by 1 bit. When you shift the contents towards left side by bit, this MSB bit will be moved to carry flag. If carry flag is equivalent to 1, it indicates a negative number. If carry flag is equivalent to 0, it indicates an positive number. So for checking the carry flag, we write JC instruction. JC L1. So what this instruction will indicate is, if after shifting this operation, if carry flag is equivalent to 1, go to the label 1. So what is carry flag is equivalent to 1 indicates a negative number. So at label 1, we are going to be write the instruction which is for incrementing the count related to negative numbers. Suppose if this condition is failed for the case carry is equivalent to 0. After shifting, let us assume if the carry flag is equivalent to 0, what it indicates? It is a positive number. So this condition will fail. So the subsequent instruction will be executed. In the subsequent instruction, we will write increment BH. So this BH, it is used for loading the count for the positive numbers. Then unconditionally we will go to the jump to by skipping increment BL, because increment BL, it is used for updating the negative number counts in the series. As one data you are done, for advanced to the next data, we go for incrementing SI. So SI will be point to the memory location of the series variable. As one data we have checked, decrement the count. So this loop we have to iterate until the count in CL register is equivalent to 0. So for that we go for checking J and Z. J and Z means if after decrementing the count, if CL is non-zero, go to loop 3. Why we are going for loop 3? For fetching the next data. So what is that instruction we use is move AL comma in brackets SI. Suppose if CL is equivalent to 0, what is CL is equivalent to 0 indicates all the data is done. All the data has been checked. So it will be go to the next instruction. What is the next instruction we are having? Loading the positive count and the negative count into the respective memory location. So for that we use the instruction LEADA comma pass. So POS is the variable name which we are given for count in the data segment. So the address we are going to be loaded into DI. Where is the positive count? The positive count is there in BH register. So the BH register contents will be moved to the memory location whose address is specified in DI register. So for fetching the negative address, we go for either writing LEADI comma neg, otherwise you go for incrementing DI. So as we are reserved only one memory location, we go for incrementing DI, or you can use load effective address DI comma neg. So this instruction will fetch the address of the negative variable which is assigned in the data segment. That address will be loaded into DI. Into this memory location, BL register contents will be moved, because the BL register contents will consist of how many number of negative numbers are there in a given series. So once this updation of count loading into the memory correspondingly for positive and negative numbers is done, we can terminate the program by calling the interrupt 21H for returning to the DOS. So we move 4CH into AH register. As the program is done, we can end this particular segment by using code endes. To end the program, we use the directive end. So which program we have to end is, which is started with the start variable. So with this, we are done the programming for finding out how many positive numbers and negative numbers are there in a given series. Next, we will move to the third program, where this third program is to find whether the data which it is provided, it is consist of even parity or odd parity. So what is this parity bit indicates is, the parity bit indicates how many number of ones are there in your data. Number of ones in the data. So if parity bit is equivalent to 1, it indicates it is an even parity. If parity bit is equivalent to 0, it indicates it is odd parity. So just we will check the parity bit either it is 1 or 0. So for that we use the instruction is JP. So when this condition is true, that is indicates even parity, true case, false case it is for odd parity. Now we will see the problem statement. Decide whether the parity of a given number is even or odd. If the parity is even, we have to set DL to 0, else DL to 1. The given number may be a multi-byte number. So let us consider instead of 8 bits or 16 bit, we are going to take 32 bit data. So first we will take 1 data. This is, I'll take byte 1, byte 2, byte 3 and 4, byte 4. 4 bytes we are checking. First we will take this data. We will see whether it is even parity or odd parity. If it is even parity, we will make DL is equivalent to 0. If it is odd parity, we will make that count in register as 1. This is CL we will take. Right. So again we check for B2. Let us assume if B2 also, we will check either it is even or odd. So then we go for incrementing here. If it is this case, increment this. Suppose one is even, another one is odd. Only corresponding registers we are going to update, not every time. After checking B2, then we go for B3 checking, then we go for B4 checking. So what could be the answer for if it is even number of ones are there in our data? So let us consider my BL data is consist of odd numbers. B2 data is also consist of odd number of ones. B3 is also consist of odd number of ones. B4 is consist of odd number of ones. For every odd number, we are going to be increment CL. So initially it is equivalent to 0. When you find it is a odd number, increment it. Again you found as odd number, so increment it. Again. So what is the value you will get? 2. So when you have an even number, after incrementing the CL, if it is even number, it indicates it is a even parity. If it is odd number, then the odd parity. See now how many odd numbers we got? 4. So 4 odd numbers if you add, again we are going to get a even number. Similarly, let us consider my data is consist of B1 is odd number, B2 byte is even parity, B3 is even parity, B4 is also even parity. So as it is an odd number, we are going to be increment CL. When it is an even number, no updation. Even number, no updation in CL. Even number, no updation. That means we are not going to add anything. So this value will be retained. So what is the value I will get? 1. So when you get an odd number, it indicates the total number of ones in our data is odd. Suppose if B1 is odd number of ones, B2 is even number of ones, B3 is odd number of ones, and again B4 is even number of ones. So here the CL count will be incremented by 1 as it is even number, no updation. Again odd number, go for incrementing it. Again even number, no updation. What is the value get? 1 plus 1, 2. So if it is 2, it indicates it is an even number. That is even parity we are having. So the simplest algorithm to check the parity of a multi-byte number is go on adding the parity byte by byte with 00H. The result of the addition reflects the parity of the byte of the multi-byte number. Adding the parities of all the bytes of the number, one will obtain the overall parity of the number. So if that particular number after incrementing, if it is even, it indicates even parity. If the count in CL register we are taking in this example, if it is even number, it indicates a even parity. If it is odd number, it is odd parity. So first we will write the program by fetching the address of the data segment into the DS register by using this instruction move AX comma data, then move DS comma AX. So these two instructions are used for loading the data segment address which is assigned by the assembler into the data segment register, that is DS. Then how many number of bytes are there that we are going to be loaded into BH register. Here we are reserving two registers. One is AL. For every time we will fetch one byte that we are going to be stored in AL register. So first we are clearing XR AL comma AL. Then the count for incrementing after checking each and every number for even parity and odd parity, we will increment the CL register. So initial count we will place as 0. So by using the instruction XR CL comma CL. So these two instructions will clear the AL register as well as CL register. Next, we want to fetch the address of the first number, that is first byte. So for that, we'll write move SI comma offset of number. So this instruction will fetch us the offset value of the number in the data segment into SI register. Then this number will be added to AL. So what is AL? By default, will take as 0. So here the SI contents, that is memory location contents, will be added to AL. So once this content is added, we will check for whether it is even parity or odd parity by using JP instruction. Jump if parity to even parity label. So what is jump is equivalent to parity is equivalent to 1 indicates it is an even parity. If this condition is tail, that means if parity bit is equivalent to 0, that indicates it is an odd parity. So when it goes to even parity, so we are going for next memory location. That is for even parity, just we are skipping this incrementing CL register as we have seen in the example. So when we are incrementing CL, if parity bit is equivalent to 0, that is for odd parity, this condition fails, so the next instruction will be executed. So we are going to be increment CL register. So once you fetch the next data, for every time we want to clear the AL register, so for that we use XR AL comma AL. Next, as one byte is checked, the byte count which is there in DH register, that we are going to be decrement by using decrement BH. So this iteration will be takes place until DH is equivalent to 0. When DH is equivalent to 0, it indicates all the bytes are fetched. All the bytes are checked. If DH is non-zero, indicate still some more data is present, so go for next byte. So we will, after decrementing, we will check whether DH is 0 or non-zero. If it is 0, come to the next instruction. If it is non-zero, go to label 1. So what we will have the label 1 is, we have to fetch the data into AL register L1 and add to the AL register. Suppose if all the data, that is all the bytes have checked, then clear the DL register. The contents of CL register, we are going to be check whether it is even number or odd number by checking the LSB. Just shift these contents or rotate these contents towards right side by 1 bit. So now this will be goes to carry flag. So when carry flag is equivalent to 1, what it signifies? Odd parity. When it is 0, it indicates an even parity. So for that, either you can use ROR, otherwise you can use SHR, or you can also use RCR. Rotate right with carry. All are valid. So I am using ROR instruction CL comma 01H. If carry is non-zero, what is carry is equivalent to non-zero indicates it is an odd parity. So go to label 2. So what we will write in label 2 is, we will terminate the program. For odd parity, we go for incrementing the digit. Here we will write this. When carry is equivalent to 0, it is even parity. Already DL is 0, so just we go for terminate the program by using move AH comma 4CH INT 21H. Suppose if it is even parity, even parity means carry is equivalent to 1. So when carry is equivalent to 0, that indicates we don't have any, we can tell it is a even parity. When carry is equivalent to 1, it is odd parity. So in that case, we go for incrementing DL if carry is equivalent to 1. It is odd parity. So increment the DL register. After that, we can terminate the program. Now we will see the entire program in single glance. So assume CS colon code, DS colon data. This is assume that too. It is for requesting the assembler for reserving the memory for code segment and data segment. Next, we will start the data segment by using the directive segment directive. So it will be prefixed with the data. It indicates what is the type of segment we are having. As it is multi-byte, we are going to use define DD, define 10 bytes. Then 335A 379BH, it is for storing the 32-bit data into the memory location. Define byte count, how many bytes we are having here. See, this is 1 byte, this is 2nd byte, this is 3rd byte, this is 4th byte. So byte count is equivalent to 04. In the program, code segment, it is for starting a segment. Segment is the directive. Which segment we are starting here? Code. Then we will load the DS register with the data segment address by using move AX comma data, move DS comma AX. How many bytes you want to check? That we are going to be loaded into DH register, clear AL register as well as CL register. AL register we are going to add every time the first number. Then we will check for parity bit. The CL register, it is for count for odd parity case. When our odd parity is there, this will increment the CL register. If it is even parity, we are not updating the CL register. So to fetch the address of the number, we use the instruction move SI comma offset of number. Offset directive is used for fetching the address of the number that will be loaded into SI. The same thing we can write by using LEA instruction. LEA SI comma num. Both are same. Both are used for fetching the offset of the variable. To find or to load the first value, we are write the instruction add AL comma SI. This will fetch the first number that will be added to AL and the result will be there in AL. So after addition, then we go for checking whether it is even parity or odd parity. If it is even parity, go for even parity label. So what we have in the even parity label is go for advancing to the next memory location. Suppose if it is odd number, that condition is false. So it won't go to the even parity label. The next instruction will be executed. What is the next instruction we are having is increment CL. Just we are incrementing the CL. So when it is increment the CL, CL is equivalent to CL plus 1 if odd parity found. Then increment SI. Then for clearing the register, either you can use move AL comma 00, otherwise you go for XORing AL comma AL. As one number we have checked, go for decrementing DH, JNZ, next byte. It is for fetching the next byte. Here we have the next byte. Or you can give any label 1 or anything. Next, for clearing the DL register, either you can use move DL comma 00, otherwise you can use XOR DL comma DL. Both are valid. So these two instructions are used for clearing the register. Then rotate the contents of CL register towards right side by 1 bit. So either you can use SHR or ROR. So this is mainly for checking LSB bit. So why we need to check LSB bit is, if LSB bit is equivalent to 1, it indicates it is an odd parity. If it is equivalent to 0, it indicates it is an even parity. So jump on no carry. If no carry is there, then you go for clearing, because already we have cleared the DL register. As per problem statement, if it is even count, so we have to load DL with a 0. If it is odd count, DL we have to place with 1. So as it is clear, you can terminate the program. Otherwise, if this condition is fails, then we go for incrementing the DL register. After that, we can terminate the program by generating interrupt 21H with the subroutine as 4CH into AH register. These two instructions are for returning to DOS. Then we can end the code segment by using the end as directive prefixed with code. To end the program, the directive is end, the program is started with a start label. So we will end the program by using the assembly directive end start. So this is a session related to a few programs related to 8086 processor. Under this session, in this session we have discussed a program for to find even numbers and odd numbers in a given series by checking the LSB bit. For checking the LSB bit, we will shift the contents towards left side by 1 bit, either go for shift or rotate operation. The second program is to find how many number of positive numbers and negative numbers are there in a given series. To check whether it is a even number or odd number, we have to shift the contents towards right side, because MSB bit will decide whether it is a positive number or negative number. For negative number, MSB is equivalent to 1. For positive number, MSB bit is equivalent to 0. The third program is corresponding to in a given multi-byte, whether that byte is consist of odd parity or even parity. Okay. Thank you all. I'll ending this session.
Like, share and subscribe. Hit the bell icon for more updates.